Or here's part 2 of the reaction mechanism worksheet. We already did the majority of it, but there's a few other miscellaneous kind of things that they put in here. And so the number one thing, as I told you in the last one, that they'll ask you if for mechanisms is they might give you like a 2 or 3-step mechanism and say, is this acceptable mechanism, number one? And then, of course, if that's the case, then when you add them up, you should get the overall equation. The other thing is, for the slow step, which we found to be 2, you should be able to derive the rate law from the rate law of the elementary slow step. The slow elementary step should be able to take its rate law and derive the overall rate law from it by doing substitution, as we talked about, if you need substitution. Sometimes it ends up being the rate law of the first one. Like in the rate law of the first, it just said NO2 2 F21, and that's the end of the problem. Right there, because if the elementary rate law matches it, or if there's an intermediate, and you can substitute it out. Okay, so the next little question here. It says number 1. I think this will be pretty easy. I hope. Sketch a graph to indicate the concentration of F2 versus time. So if they had to make a concentration of F2 versus time, what would that graph look like? Well, we know it's just going to be decreasing as time goes by. You see there. Now, if number 2 says sketch one that would confirm the order of the reaction with respect to F2. Does this say A and B, or it says F1 and F2? So this is number 1, F1. How can we just take that away? Oh yes, all the way. If I need this, I can go back to my other problem. F1, F2. How can you confirm that it's F2, which is first order? Well, then you know that. You take the natural log of F2, concentration, versus time. Now, they like to do this on the AP a lot. They'll just say, like it just said there, sketch a graph that would confirm, that would prove the order of this reaction with respect to F2. And what you would have to do is write the natural log of F2 versus time. If it's first order, will give you a straight line with a negative slope. You've seen that. All right. Then it says for G, sketch a graph to confirm NO2. So for NO2, it's the same thing. It's a reactant, so you expect it to go down as time goes by. Now, since it says 2-to-1 ratio, if they had you sketch them on the same graph, like whatever fluorine goes down, NO2 should go down double that. Like if this were, just say that was 0, and that was, I don't know how to do that, 2, 4. Yeah, say that was 0, and that was 2, and that was 4. Like 1, 2, 3, 4. Okay. Like 2 was, say it went down pretty much to level 2. Make it easier for me here. And it just say, well, I'll make it a little bit shorter. It started at 4, it went to 2. Okay, well, NO2, if it started at 4, we're just assuming it would have to go out all the way to almost to the bottom, pretty much at 0, but it wouldn't be 0 all the way. So it would have to go down twice as much as that one. And that's not a big deal, but it would just curve down. They probably would have you put it on the same graph. F2 here, and then NO2 going double as much, because it has a 2. 2 for every one of those. Two of these are needed for every one of those. Okay. Now, 2 of those are used up for every one of those. Another way to look at it. 2 of these are used up for every one F2. Then, what would indicate its graph? Well, since NO2 is second order, then that means that it will be 1 over NO2, or NO2 to the negative 1 power versus time. Will give you a straight line with a positive slope going up like that. Okay. All right. There's another thing they ask you. H. Indicate how to determine the half-life using the graphs F and G above. You may simply make a label on the graphs, on the applicable graphs. I showed you this already on the other video that came before. You've already seen this. I've already gone through this on the 12-5 part 3 video, if you want to go back and look at it. But anyway, what you could do, the half-life would be the time it takes, whatever the initial concentration, like for this graph, if we start at 4, that kind of works out good, 4 to 2. The time it takes to go down half, that would be the half-life. So if this is at 4 at time 0, then the half-life would be the time it takes to get to 2, which is, I guess, where the line's going to end up here. So just right about here, and then it gets to be a straight line. Why does it get to be a straight line, by the way? Well, that's the next chapter of chemistry. Don't worry about that yet, but it does get to be straight as long as the system is closed. But anyway, we'll get to that later. So once you get to 2, which is probably about here, then it becomes kind of straight. It's all 2, 2, 2, 2, 2. But the first time you see 2, that will be the half-life right there at that time. Or on that graph, the same thing. Well, actually, half-life would be the time from 4 to 2. So you could say from here to there. So that the half-life of the NO2 would be from time 0 to where you get to 2. Not all the way down the bottom. The time it gets to half the original concentration. Or you can say, take the slope of this line, and since it was first order, slope of the line, then say it's 0.693 over K. Plug it into there. But for this one, you can find the slope of the line, but then you got to plug it into the second law equation. NO2 -1 final equals KT times NO2 -1 initial. And for the initial, put in 2 maybe, and put in 1 for the final, and then plug in K, and then solve for T. So again, watch part 3 video, and I explain that more in depth. So that's the way you can do it. All right, letter I, it says this. Assume that all the graphs we've done here represent catalyzed reactions. Uh-oh. So, because we had a catalyst, but we didn't show you. Assume these are catalyzed. So, what I'm going to do, because I kind of know what's coming up on this, this is catalyzed, 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 catalyzed. They just tell me that. Now, and they've done this before, to each graph, add a curve or a line, maybe a different color, and I'll use orange, to show what would the uncatalyzed reaction look like. Okay, remember, catalyzed makes the reaction go faster, okay? So in other words, if you started at F2 and it took you, I don't know, 4 minutes to get to this point right here, okay? If you had a catalyst, it took 4 minutes. If you didn't have a catalyst, it'll take even longer to get there. So what that would mean is it would be... well, hold on. Let me see another way to put it. Oh boy, it'll be like this. I'll just do something like that. Okay. So, well, I don't even know if that's not really a good graph the way I did that. Well, it should take a longer amount of time to get to that same level. That's the point I'm trying to get at. With the catalyst, I don't know. The graphs look so bad. Okay. Should be a curve. Just put a curve above it. But the point is, how long did it take to get to any number? Like, I just used 2. It was 1 point, but we'll just use that point. To get to this point in time, it took this much time with the catalyst. But with the uncatalyzed, it took you this much time before you got to that level, whatever that level is. Okay? So the point is, the uncatalyzed would be longer. The curve is going to be above it. Same thing here. I don't even know if I could draw it there, could I? Yeah, I guess I could. It might look better on this graph. Something like that. You don't have to go all the way down, but it would be, that graph curve would be above the other. Uncatalyzed, uncat, and cat. Now, when you do the natural log, it's going to be the same thing, actually, because you see as you decrease the natural log at any point, it's also going to get smaller and smaller. So, uncat would be a line like that, would be above the other. The slope would not be as abrupt, again, the same way as it wasn't there. And then for this one, though, it'll be interesting, because for this one, the catalyzed, the uncat, okay, for this one, you've inverted it, right? So the uncatalyzed is on top here, but for a second order, the uncatalyzed would have to be on the bottom, like that. Because, as I said, you invert the numbers to do that. So, anyway, All right, let's just see what's next in here. And the way this works, like on an AP exam or test or whatever, they normally just ask you one of these graphs only. They don't ask you all four of them. I'm just trying to give you everything that has popped up somewhere, either on the test or sometimes even from your textbook. I look at things that are in there, and Zumdahl is really good in their textbook about predicting like what kind of stuff the AP might like to ask. Okay, let's see what's next on here. I think we're almost done. Letter J says, assume this reaction is endothermic. Sketch a potential energy diagram, PE versus reaction progress. Okay, so potential energy versus, a lot of times they'll say reaction coordinate or reaction progress. And all this means is, it's again kind of a theoretical thing. How long along the way, from the beginning to the end, how long did it take to form the activated complex, the rate determining step, and go on after that? So here's how I'll do it. First, you need to know if it's endothermic, if NO2 plus F2 plus NO2F were endothermic, then wherever you start, if we go like, let's say I start right here, about kind of like a little bit lower than halfway. So I'm going to go up to a high point, going to come down, but then I'm going to stay higher than I started with. Okay? I guess I can make that a little bit more straight. Like that. Okay, so now here you start off with NO2. In fact, if you want to put NO2 plus NO2, you could put that. If there were two reactants, you could put those there. Then here, it's now all become 2NO2F. I'm sorry. That's not good. That's not good. 2NO2 plus F2. I could put NO2, NO2, and F2, but for a moment I thought the reaction was only NO2 plus NO2. That's a different reaction. Okay, yeah, it's better to put 2NO2 plus F2 there. So at this very beginning, you had two chemicals separate in those amounts, and that's what you add together. And at this point, you have NO2F, the products. Now, what do they want you to label on this? It says show the axes. It's very important. Here's potential energy, and here's the reaction coordinate. Just like on the other ones we drew, make sure you put natural log of whatever it was, F on one side, and then concentration, natural log of F concentration and the time. It's very important to tell what they are. They like to say sketch graphs. They don't always make you actually plot points, and that takes a little bit longer. They've done that before, but they have not. But a lot of times they're going to say sketch. What should it look like? And they say, oh, that's higher than that. That gets you a point right there. And the axes, the energies of reactants and the products, relative energies, they would say, there and there. Now, they might tell you, I don't think they're going to give you numbers. They could give you a graph and it would have numbers in it and then have you read something. What else do they want you to find there? All significant energy differences. Well, that's what I call it. But okay, so when we start here, from here to the highest point, remember what that's called? EA, activation energy. That's the energy like what you need to add to get the reaction going. Now here it's a very high reaction activation energy. You got to keep doing it. And this from here to there, that will be delta H. The enthalpy for the reaction will be wherever you started to the highest point. And obviously it's a positive number because you went up. If we're going down, exothermic, you start lower than you began. Here you end up higher than you began. In fact, you might put positive delta H just so you know that. Activation energy will always be positive. Okay, by the way, too. That would be just a little thing to add in. Let me see, is there anything else? Good gracious. Okay. Oh, okay. The energies, okay, number 3. The energy of the activated complex. Okay, activation energy is where you form the activated complex. So this would be the activated complex. Same thing. Now in this reaction, if I can remember what it was, I don't know what, though they didn't really show an activated we had an intermediate NO, in this one we had F was an intermediate that joined NO2F, and then you form NO2F at the point later on. Well, I don't know what that would have been right there. Perhaps an activated complex might be when you have NO. Well, don't even worry about it. But sometimes there could be a formula there actually to get to an intermediate. But in this case, it could be the NO. You have the NO2. What did we say? NO2 with F2 gives you NO2F. That's one of the products, and an F left over. So it could be that the second step. The second step was a slow one. So NO2 to form with F. So when NO2 is about to go to join to an F, maybe don't worry. You can put that there if you wanted to. I mean, that's actually a product too, but that was what was the activated complex when it joined with the intermediate. And then it stuck. That was enough energy to collide efficiently, enough energy that it sticks, and then you're down the hill. Okay. Then it just says add a line or a curve, it'd be a curve in ink that shows the potential energy for an uncatalyzed reaction. Okay, so if this is catalyzed right now, so this is catalyzed, remember this is how much energy it takes. All right, if it's uncatalyzed, another definition of the catalyst, it lowers the activation energy. So the catalyzed reaction should go the same path, but it should go higher. It should be, as much. It doesn't matter how much higher you want to make it. But the point is, I'll put the uncat will be the orange again. So the uncatalyzed is going to take more energy, higher activation energy than the catalyzed. And usually it'll be significantly more. Like maybe the catalyzed might be like down here, but oh well. But I just drew it that way. And then otherwise it will follow the same path. Same beginning and same end. And the same delta H. It doesn't change the delta H. It just changes lowers the activation energy. A catalyst lowers it. Uncatalyzed will have a higher. Okay. This is a lot of stuff, but as I told you, this is some of the more advanced stuff too. So I'll tell you this, that when you take an AP question, if they ask you something about like method of initial rates, find the power for F2 and for NO2, or they give you a graph to find the power. Then after that, they could if you can answer all of that, if you can get to the rate law, find these powers, these orders, find K and its units, you pretty much have passed that. Like you pretty much got a 3 on that question. But then they're going to add some more questions. They could ask you to sketch graphs. They could ask you about the mechanism, as I told you as well. And that's where you can get, being able to do mechanism, everything on this worksheet. If you can do everything on this worksheet, that's where you can get like a 4 or a 5, I'd say. But they could still ask you some of these things in multiple choice. So it's worth a lot to study this and to know it. But we're getting really near the end of the big material. All right, thanks a lot. I'll see you guys. I hope that helps you out. So just do the whole other worksheet, and it's going to be almost exactly like what I showed you. But you'll see different formulas, different chemical reaction, and there are some other problems. I might also give you some little bonus, little mechanism problems if you really want to play around with them a lot. So I'll tell you about that later on. I'll see you.